So let's talk about liquids, okay? So in 105, we all talked about the states of matter. And we even talked about it a little bit, I think, in day one in this class, about what the differences are, right? So real quick, you guys remind me, how do you distinguish the difference between solid, liquid, and gas?
Available space.
Okay. Okay, I like it. So if I have a solid, a liquid, and a gas, and we have all that in this room, right? And this room is 71 degrees, because I just checked the temperature over there, okay? Then the average kinetic energy of all three of those things is the same, right? So temperature, remember, is the measure of the average kinetic energy. Everything in this room, except for you guys, are the same temperature as the room. So they all have the same energy. So the energy thing is not quite there, but you're really close, okay? So what is another way we can distinguish between solids, liquids, and gases, other than the fact that, you know, that's solid, right? So shape is a big deal, right? Solids always have that shape. Whatever that shape is, that's what it is, right? Liquids have the shape of whatever you put it in, right? If you put water in that water bottle, it's roughly spherical or cylindrical, right? But if I put it in a coffee cup, then maybe that's different, right? Why is that? Why do liquids assume the shape of their container? They're still in close contact. You're on the right track. Molecules in a liquid are still in close contact, just like they are in a solid.
They're able to move around.
But they're able to move around each other. That's the thing, okay? They're able to actually, they've got enough energy to overcome some of the forces that are holding them in place. And so they're able to freely move around. They've still got to stay in contact, but they can move around each other. Solids don't, right? Solids are stuck in place. Here's a solid atom or molecule. Here's a solid atom or molecule. They're not moving around each other. They're stuck close together like this, and they can wiggle, but that's it. What's that?
What's Jello?
Jello is a colloid, and we'll talk about those in the next chapter.
What about non-Newtonian?
So solids are easy to deal with. We can explain solids pretty well. We can define them by their rigidity. We can define them by their length, width, height. We have a branch of physics called solid state physics where we can do all kinds of fancy stuff with solids, okay? Gases are also reasonably easy. They're probably the easiest. We got PV equals nRT, and that explains like 90% of all gases, okay? And then we've got 25 other equations that we can use to explain gases when they have intermolecular forces that we got to deal with and stuff like that. Liquids are the most difficult to describe, right? Because they're in constant contact with each other, but they got enough energy that those molecules are moving around each other. We don't have an equation of state for a liquid, right? I don't have a PV equals nRT that defines a liquid. So what we can do is we can do a bunch of computer simulations and calculations, and we can calculate properties of liquids that way, but that's hard, right? Say again. Everything is always moving at the molecular level, right? Even solids, right? So even in this thing right here, those plastic, molecules, each atom in that plastic molecule is wiggling in there like this right here. They just can't go anywhere.
That's why old glass has like bubbles and warps.
That's a different thing.
Okay, I love it. I tried.
Yeah, that's a different thing. So that's a function of the actual creation of the glass itself.
Okay.
Yeah. So solids, again, we usually have some sort of order to it, and we'll see that in the next chapter. We have, here's an atom, here's an atom, here's an atom, here's an atom, and we can copy and paste that structure, right? We can have a crystal out of it, right? That has a nice periodic arrangement. Liquids don't have that. And so the interaction between this liquid molecule and this liquid molecule is different than this liquid molecule and this one that's closer together, right? So trying to calculate all those forces is very hard to do. Yeah, this is the reasonable example of what solids, liquids, and gases look like at the atomic level, right? We got this nice ordered thing, close contact for the solid. We got pretty much close contact, a little more space, but disordered in a liquid. And then gases, right? So molecules are in constant motion. close together, so the intermolecular forces matter a bunch. And because they're close together, they're not really compressible. Right? So one of the things that we care about when we're talking about liquids is converting it to either a solid or to a gas, right? So evaporation, condensation, these are things that we can measure for a liquid. They're easy enough for us to talk about in this class, and they relate to those intermolecular forces that we've been talking about. So we're going to talk about it, okay? Anytime that we are converting states of matter, right? Anytime we're going from a solid to a liquid, or liquid to a gas, or solid to a gas, or any combination you can think of there, it's a play on intermolecular forces, okay? That is really what determines the state that you're in. Are we solid, are we liquid, are we gas? It's a balance between how strong is the intermolecular forces holding these things together versus how much energy do I have from the temperature of that thing right now, right? So again, the hotter it is, the more energy there is, the faster those molecules are moving, the more energy those molecules have, versus how much energy is holding them together, right? So think about it as solids would be like you holding two newborn babies, okay? They're gonna wiggle a little bit. You got them under control, right? Liquids are like you holding two 6-year-olds by the hand, okay? They're everywhere all the time, but they're still connected to you, right? Gases would be like you talking to your friends. So what happens in evaporation? You've got to have energy put into the system. You have to break the intermolecular attraction that's going on between the molecules in order to get one to fly off into the gas phase, okay? That's a function of how fast is that molecule moving, right? And we know that there's a distribution of speeds. We talked about that last time. So for any given temperature, there's something that looks like this, right? This is the most probable speed, but some molecules are going to have this speed, and some molecules are going to be lazy and have this speed. So there's always some fraction of molecules that have enough energy to go into the gas phase. As we increase the temperature, that fraction of molecules gets higher and higher and higher. Because we're having to put energy in order to overcome those intermolecular forces, evaporation or boiling is an endothermic process. Delta H is positive. You remember that from Gen Chem 1. This is a thing that requires me to put energy in, okay? So again, the condensation thing is exothermic. We're creating intermolecular attractions. And anytime we do that, we go to a lower energy state. If we go to a lower energy state, the energy's got to go somewhere. It goes out into the surroundings. And like I said, there's always going to be some number of molecules that have enough energy to overcome those intermolecular forces and to be in the gas phase. Okay. As we increase the temperature, in this case, the blue line, temperature 2, is higher than temperature 1. And we can see that there's a greater number of molecules by this much that are able to move into the gas phase. So now we got to talk about the concept of boiling point, right? So boiling point of water is 212 degrees Fahrenheit or 100 degrees C. But what does that really mean when we say something is boiling? So that's the thing that's happening. That's the phase transition that's happening, right? That's the evaporation that's happening. But how do you know? If you put water on the stove, right? How do you know when it's boiling?
It's got bubbles.
Okay.
Yeah, like the vapor.
Turn it from a liquid into a gas, for sure. But isn't it doing that before it gets to the boiling point? Right? We can see steam coming off of it for a long time before we ever say, quote, it's boiling, right? So how do we know it's boiling? Well, that's a good point, right? It actually works out if we were to measure the vapor pressure. Do you know what that means? I'll say the word vapor pressure. Maybe not. So let's talk about that first. Then we'll talk about boiling, okay? Put that on hold, all right? Okay, so we can quantify the amount of energy here. So we're talking about this whole got to break the intermolecular forces to go into the gas phase, or as this thing flies down and touches this, they're going to create intermolecular forces and we're going to condense. There's an energy associated with that. That energy is related to the intermolecular force that's there. And we can define that, we actually define that as the enthalpy of vaporization, right? So the enthalpy of vaporization is the amount of energy required to turn a liquid into a gas. It depends on the type of intermolecular force that's present, and it's directly related to boiling point. If you've got weak intermolecular forces, you've got lower boiling point, and you have a lower enthalpy of vaporization. Right, water has hydrogen bonding that's really strong. Water has a boiling point of 100 degrees C and has an enthalpy of vaporization of 40.7 kilojoules per mole. Condensation is the opposite process. Do you agree with that? So condensation is going from a vapor to liquid and energy. Okay? So condensation is the same number there. It's just a negative sign. It's exothermic. Right? So when I condense steam into water, this number is the same, but the value would be negative. Okay? That means it would be giving off 40.7 kilojoules per mole of water that we condense. That's right. That's why steam burns you. It's the condensation that releases heat that's actually burning you. It's not the fact that it's 212 degrees. That may play a minor role, but most of the energy is coming from the condensation. So we could write it this way. Right? The enthalpy of condensation is just minus the enthalpy of vaporization. Right? Same value, just opposite in sign because we've effectively switch the direction of the chemical reaction. This is something that's very similar to the stuff we did in chapter 6 of Gen Chem 1, so let's kind of remind you here, okay? If you've got 925 milliliters of water, you put it in a pan. We're not considering how much energy it takes to heat it up. We just want to take it from 100 degrees and evaporate it. How much energy does it take to evaporate the water? How would we approach this problem? What information do we need to know? We don't have all the information we need to solve the problem written. Okay? So what information will we need in order to be able to solve this problem? Okay, that's good. We need that. And luckily we know that. So for water, delta H of vaporization is 40.7 kilojoules per mole. So with that, is that enough to solve the problem? Is that all the information we need?
We need pressure.
I don't know. Do we need pressure? That water that you're looking at is liquid water. That's not water vapor, okay? So this is not an idle gas law problem. That's liquid water. I like it. We need the molar mass. Molar mass of water is 18.02 grams per mole. Okay, so if we're looking at that, if we're tracking the units, I got moles here. That's going to relate energy to moles, okay? I've also got moles here, so now I'm relating energy to grams. I don't have grams. How am I getting grams? Right now I got milliliters. I need a relationship between milliliters and grams. That's right. Density works. So what is the density of water? Well, density is a function of temperature, but the density of water at roughly room temperature, or even up there at 100 degrees, is basically 1, okay? So we can say, for simplicity's sake, here, the density of water is going to be 1 gram per milliliter. Now, with that information, do we have everything we need to solve the problem? So you can see how this is a Gen Chem 1 problem. Right? We didn't do anything any different than we've done in Gen Chem 1. But we ask you a problem without a complete set of information, and we ask you to go dig up the information. Okay? That's the difference. So now it's more than can you solve the problem. It's do you understand the information you need to solve the problem. That's a harder thing to learn. So how do I solve it now that I got all the stuff I need? Okay, so 925 milliliters, I'll start there. Where do I go from there? So tracking the units, milliliters cancel, grams cancel, moles cancel. I'm left in kilojoules. I was asked to find energy. We know energy is in kilojoules. That should solve the problem. 2089, 2089. Is that what you got? Can I get a confirmation on that? 2089 kilojoules. Yeah, that would be something I would give you. I wouldn't expect you to remember the heat of vaporization or even the density, really, right? Right. And you can calculate molar mass, right? You've got a periodic table. That's not an issue.